In this video, I will discuss about the time period of a simple pendulum whose length is very large. In fact, its length is so large so that it is in fact greater than the radius of Earth, far greater than the radius of Earth. So let us consider such pendulum whose length is far greater than the radius of Earth, and therefore its suspension point would be out of the Earth, and this is the suspension point of such pendulum. Now this is the Earth and this is the radius of Earth. So let us consider a ball of mass m which is connected to a string of length L which is suspended from this point which is outside the Earth. Now we have to find out the time period of small SHM of this ball. Now we are also considering the fact that L is so large so that this theta and this alpha is very small, and we are also considering the SHM of small amplitude. So theta is also small. So starting with the free body diagram of the ball, this is tension T, this angle is theta. Now the component of T is T cos theta and this component is T sin theta. This one is T sin theta. Okay, so the component, let's suppose that mg is acting in the downward direction. Obviously we are considering that the acceleration due to gravity is g, because this pendulum is very closer to Earth as this angle is very small. So the component of mg in the downward direction is mg cos alpha and this component would be mg sin alpha. So you can see that the component of t cos theta will balance out mg cos alpha, and for small alpha and theta, T will be equal to mg. Now the restoring force is the force which is bringing back this ball to the mean position, and this position is the mean position. So the restoring force will be T sin theta plus mg sin alpha. Now T and mg are equal, so T is equal to mg, and taking mg common, then it is sin theta plus sin alpha. Now if angles are small, sin theta and tan theta are also equal. So you can see that sin theta will be approximately equal to this x upon L. You can see from this triangle that sin theta will be approximately equal to x upon L. So this is x upon L, and sin alpha will be approximately equal to x upon r, because this distance is almost equal to r for small angles. So we are substituting these assumptions over the restoring force, and therefore restoring force would be mg x by L plus x by r. And now restoring force is always equal to m omega square x, where x is the displacement of the particle from the mean position. So cancelling this m with m and x with x, omega will be equal to under root of g into 1 by L plus 1 by r, and the time period t will be equal to 2 pi into under root of 1 upon g into 1 upon L plus 1 upon r. Now you can see that if, now I am writing the time period again on this page, t is equal to 2 pi under root of 1 upon g into 1 upon L plus 1 upon r. Now if r is very greater than L, which means that in practical pendulum, which is the pendulum on Earth, the length of the pendulum string is very less than the radius of Earth. So 1 upon r would be very, very less than 1 upon L. Therefore, we can neglect 1 upon r, neglecting this. So T would be equal to 2 pi under root of L by G. This we already know. And if this L is very, very greater than r, then 1 upon L will be very, very less than 1 upon r, which means that we can neglect 1 upon L. So neglecting this 1 upon L, we can see that time period will be 2 pi under root of r by G, which is also equal to 84.6 minutes. So this is the this general formula is the time period of a pendulum of very large length as compared to the radius of Earth. Thank you.